In this video, we start looking at column buckling. We first look at a column which we assume to be perfectly straight, although this is not realistic, but as a simple starting point, that is pinned at one end. It's also pinned at the other end, but is free to displace in the vertical direction. And we apply an axial compressive load P, and we do the following experiment. We keep increasing P a little bit each time, and each time we increase P, we disturb the column slightly in the transverse direction. So in this direction. And when we do that, the column will oscillate in the transverse direction and settles down at this. When it settles down, we see what the transverse displacement delta is, and we plot. So we generate a plot like this with the transverse displacement delta and the axial force P. So for small values of P, if we disturb and let go, the column will come back to its vertical position. So the transverse displacement will be 0. But there comes a time when the axial load is sufficiently large, we let go, the column settles at a new equilibrium position that is bent. And then for subsequent larger axial loads, we don't even have to disturb the column in the transverse direction. It will simply bend more and more. So larger and larger transverse displacements. So if we connect all these points together, we get a curve that looks like this. And this point, where the column is not anymore in vertical equilibrium, has an axial load P sub CR, which is called the critical buckling load. At this load, the column is set to buckle, which means the vertical equilibrium position of the column is not stable anymore, and the slightest disturbance causes it to reach equilibrium in a bent configuration. For a pin-pin column, such as this, this critical buckling load, P critical, is given by the formula pi squared EI over L squared, and this formula is due to Euler and is called Euler's formula, Euler's buckling formula. Now, if the column were not perfectly straight to start with, and if there were some slight imperfection, as shown here, then this curve in the P delta space isn't like this, but as soon as we start applying the load, the column will start to bend. So the curve would be something like this, rather than this ideal curve of being vertical and then developing transverse displacement. By the way, L is the length of the column, and EI are the modulus of elasticity and moment of inertia of the column. So to understand this formula, let's just build some intuition. Let's take two members, one like this and apply an axial load, and another which is longer, same cross section but longer, again subject to an axial load, so that, for example, this column would buckle in this shape. From intuition, we see that the longer column will buckle more easily, or the longer column has smaller critical buckling load. So L must be in the denominator, of the buckling formula. So we see that as L increases, P critical decreases, and we notice here that L is indeed in the denominator. Similarly, let's take two columns, same length, but one is stouter than the other. Subject to axial load again. So again, intuition says that stouter column is harder to buckle. So the stouter column has larger critical buckling load. So I must be in the numerator. And that's what we find here, that I is in the numerator. Lastly, if we take two columns, same cross section, same length, one made out of steel and the other made out of plastic. Again, intuition says that plastic column has smaller critical buckling load. So the modulus of elasticity, E, must be in the denominator, must be in the numerator. And indeed, E is in the numerator. So we kind of understand the intuition that goes behind Euler's formula. In the next video, we'll look at what if the support conditions aren't pin-pinned, but something else.